So continuing on from last class session, we were discussing isotope notation. So this is on page 38 of our notes. So let's do a refresher example just to make sure we're familiar with the concepts covered in isotope notation and just to get us back up to speed with this process. So we're asked to write the isotope symbol for an element with 92 protons, 143 neutrons, and 91 electrons. Okay, so we know that the number of protons is equal to what is known as the atomic number, and each unique element has a unique atomic number or number of protons. So if we look in the periodic table, I'd like everyone to just take a moment and find the element with an atomic number of 92. Which element has an atomic number of 92? So you're going to look in the periodic table for an element with a 92 above the element symbol. And which element?
Uranium?
Yep, exactly right. Perfect, perfect. So now we have our atomic symbol. Now we're going to need to fill in the rest of our isotope notation. So we're going to need to calculate what is known as the mass number, which is equal to the number of protons plus the number of neutrons. So then this gives us a mass number of 92 plus 143, which gives us a mass number of 235. Finally, we'll need to calculate the charge, which is defined as the number of protons minus the number of electrons. And that in turn gives us a charge equal to 92 minus 91, or a charge of +1. So we put the charge in the upper right-hand corner, we put the mass number in the upper left-hand corner, and the atomic number goes in the bottom left-hand corner. So this would be the complete isotope symbol for uranium-235. So, what I want us now to work on is to take a moment and let's spend about 3 to 4 minutes on the following two examples. In the first case, you're going to write the isotopic symbol for an isotope of sulfur that contains the same number of neutrons as silicon-28. So I want you to think about, for sulfur, what information do you know about sulfur? And for silicon-28, I'd like you to unpack this isotope notation, and from that you can figure out the number of neutrons. In the second example, you're going to calculate the number of protons, electrons, and neutrons for a nitrogen-14 atom that has a -3 charge. So we'll work on both of these examples for about 4 to 5 minutes. Don't be shy to share your responses in the chat. And if you're unsure and if you have a question, don't be shy to ask a question in the chat or verbally. And we'll discuss this example in about 4 to 5 minutes. And don't be shy if you have any questions to ask them in the chat. These are some review examples just to get us back in the pattern of calculating and dissecting isotope notation, to figure out protons, neutrons, and electrons, and to develop the skills to write out atomic symbols in isotope notation. So let's keep working on these examples, and don't be shy to share your proposed responses in the chat. And we're seeing some reasonable responses in the chat so far. Let's try to get a few more responses. And don't be shy even if your responses disagree with your classmates. It's important to share your response to help both give me a sense of your logic and so that you can then go back when we go through the problem and assess and analyze your own logic in detail. And don't be shy to share your responses for either of these two questions, and we'll discuss in about 3 to 4 minutes. And if you're unsure, don't be shy to ask a question. That's more than reasonable for participation, and it can help me provide feedback so that you can complete these problems, as these are very similar to problems you'd see on your quiz or an exam. And the responses I'm seeing in the chat look reasonable so far. Let's keep working on this example and we'll discuss in about another 1.5 to 2 minutes. And don't be shy to share your responses in the chat. I just want to make sure everyone has enough time when working through these problems. And we'll discuss in about another minute. Okay, so let's discuss this example. So first we need to unpack silicon 28. And what is this number 28 representing? What is this number 28 representing? Yep, it's representing the mass number, okay? So then, if we also look up silicon in the periodic table, what is silicon's atomic number? What is the number above silicon? What is silicon's atomic number? 14. So then we can solve for the number of neutrons in silicon 28 by taking the mass number minus the number of protons. And we know that our atomic number is equal to 14. So we have 14 protons. Ergo, the number of neutrons that we have is 28 minus 14, which gives us 14. So to figure out, so this isotope of sulfur, we know it has the same number of neutrons as silicon. So our number of neutrons is equal to 14. Okay. Now, if we look up sulfur in the periodic table, how many protons does sulfur have? 16. Yep, that's the number above sulfur. So then that would give us a mass number of 16 plus 14, which is 30. So this would be sulfur 30. Does this first example make sense to everyone? Does this first example make sense? Okay, let's look at this second example now. So we're asked to calculate the number of protons, electrons, and neutrons in a nitrogen 14 atom that has a -3 charge. Okay, so unpacking this into traditional isotope notation, we have our mass number, we have our charge. If I look up nitrogen in the periodic table, what is nitrogen's atomic number? How many protons does nitrogen have? 7. Okay, so we know that our number of protons is equal to 7. We also know that our number of neutrons is equal to our mass number minus the number of protons. And what is our mass number in this case? What is our mass number in this case? 14. So we have 14 minus 7. That gives us 7 neutrons. And then for our number of electrons, this is a review of the chapter 2 notes in Canvas, and we're continuing to go through our lecture notes, and we're on page 39 just as a reference. So for a number of electrons, we'll take the number of protons minus the charge, which gives us 7 minus -3, which gives us a total of 10 electrons. So we have a total of 7 protons, 7 neutrons, and 10 electrons. Any questions on this example from the chapter 2 notes? Okay, let's keep going. So our goal for this problem is to write the isotope symbol for an isotope of copper that has 3 more neutrons than copper 63. Now, if we think about what this mass number represents, so if the mass number is equal to the number of protons plus the number of neutrons, what happens if we have 3 more neutrons? What happens if we have 3 more neutrons? Will our mass number go up or down? Up, right? So if I add 3 to this, what's gonna be my new mass number? If I add 3 neutrons to my mass number of 63, we get copper 66. Now, the reason why I'm showcasing this shortcut is you don't always have to break the isotope notation down in so much detail. Think about what information you know, what equations you can use, and try to think if there's a more efficient way. If you're in doubt, you can take the longhand method. But I always try to teach time-saving problem-solving methods because for this problem, as we can see, if we think a little bit closely about what the mass number represents, we can save ourselves some time. Does this make sense to everyone? Is everyone comfortable with isotope notation?
I'm sorry, how did you get the copper 66 again?
So we start with copper 63, which has a mass number of 63. This mass number is telling us our protons and neutrons. So our protons and neutrons is 63. If we have 3 more neutrons in this other isotope, our mass number will go up by 3, right? Because we've added 3 neutrons to our total. So then, if we're calculating our new mass number, we'd take 63 and then add 3 to it, and that gives us 66. Does that make sense?
Yes, thank you.
Perfect. Perfect. Any other questions I can address? If not, let's keep moving on now, and let's refresh our key definition of an element. So this is another definition of an element that you'll need to be familiar with, and it's probably one of the more useful definitions. An element is an atom with a unique number of protons In other words, a unique atomic number. So each unique element has a unique atomic number and a unique symbol. Those two are closely tied to each other. Each symbol matches a unique atomic number. Okay, now we've been sort of leaving this off to the side, but this number below our element symbol is known as the average atomic mass. And that begs the question, the average of what? And this is where we're going to need to talk a little bit about isotopes in nature. So isotopes and isotopic abundance. So isotopes, as we've seen before, are the same element with a different mass number and number of neutrons. So for example, we can have oxygen 16 and oxygen 18. Does everyone notice how these two elements are the same? They're both oxygen, but they have a different mass number. Does everyone see that distinction? Isotopes, same element, different mass number. Now, if we are looking at a sample of an element, we can actually separate and study the different isotopes present in that sample via a technique known as mass spectrometry. You don't need to understand how mass spectrometry functions, but I just want you to know that we can detect and measure the amount or the relative amount of each isotope in a sample. So for example, if we're looking at a sample of chlorine gas, which is Cl2, we can look and we can separate the samples based on their mass. So we can differentiate and we can tell the relative amount of, for example, chlorine 35, which I'll call my isotope number 1, and chlorine 37, which is isotope number 2. And the height, the height of this peak tells us the relative amount of each isotope. So my question to you is, do we have the same amount of chlorine 35 and 37 just looking at the height of this readout? Do we have the same or different amounts of each isotope? So looking at these two readouts, do we have the same or different amounts if the height of the peak corresponds to the amount of an isotope? We have different amounts, right? And which isotope do we have more of in natural abundance? Which isotope do we have more of? Yeah, we have more chlorine 35. We have way more. It's almost a 3-to-1 ratio. So the relative amount of each isotope tells us and can give us a sense of the relative amount of each isotope in nature. Okay, so the majority of the isotopes of chlorine 35, the majority of the isotopes of chlorine in nature will be chlorine 35. Now, we can even calculate the percentage of all atoms of that element that are a specific isotope. And the key thing I want you to know from this discussion is isotopes are present in different relative percent abundances in nature. So for example, we clearly see we have about 3 chlorine 35 atom for every 1 chlorine 37 atom in nature. Now, you can estimate the abundance. You can estimate the percent abundance of chlorine 35 just by comparing the relative peak height. So we have a height of 3 compared to a height of 1 for chlorine 37. And that gives us a percent abundance of roughly 75%. And the way that we estimate about 3-to-1, this readout is around 75, this readout is around 25. So we have a 75-to-25 ratio, which is about 3-to-1. I'm not going to ask you to give me exact percent abundances from these charts. I just want you to be able to look at these charts and say, what is the percent abundance roughly? And it's roughly 3 to 1 or 75% for chlorine 35. Does that make sense?
I have a question. So for the total of the two isotope, it should add to 100, right? So
Yes, and we'll talk about that actually momentarily, but if you add up the abundance of all of your isotopes, it should be 100% if you're accounting for every single isotope in nature.
got it. Thank you.
Mm-hmm. So, as your classmate has alluded to quite observantly, the total percent abundance is equal to 100%. So then, if you add up the percent abundance of each of your isotopes, so the percent abundance of chlorine 35 plus the percent abundance of chlorine 37, you will get 100%. So then we can actually test that. The percent abundance for chlorine 35 is 75%. For chlorine 37, it's roughly 25%. And as we see, both of our percent abundances add up to 100%. Does this make sense to everyone? So if we're accounting for all of our isotopes, the percent abundances should add up to 100%. One moment. And if you have any questions, don't be shy to unmute and ask your question verbally or in the chat. So let's look at another example. Let's look at another element, and let's just estimate the percent abundance for each isotope of boron. So the bottom readout tells us the mass, and this top readout tells us the abundance. So what two isotopes do we have for boron, which has the symbol B? What two isotopes do we have for boron? We have boron 10 and boron 11. Okay, perfect, because we have 10 and 11. And which isotope is more abundant in nature? Which isotope has a greater abundance? Boron 11. Yep. And so we're going to read out this value, and this next calculation you're not responsible for, but it's a useful tool to know for eyeballing the relative abundance. So the relative abundance, so we have a relative abundance of 100 compared to a relative abundance of roughly.
Is anyone else cutting out really bad?
Roughly 20. Is everyone able to hear me
Yes,
okay?
it's very choppy.
Let me try one thing. Allow me 1 second. How is it now? Is it
Sounds better.
okay? Perfect. Sometimes if multiple things are on the screen, the audio quality can go down slightly. So just to repeat, we traced out the relative abundance of boron 11 and boron 10. So reading off, we have a relative abundance of 100 to 20. If we're calculating a percent abundance, we take our relative value over the total. And the total in this case is 120. So we take 20 over 120 for boron 10, And this in turn gives us a percent abundance of roughly 17%. Well, for boron 11, we have 100 over 120 times 100%, and that gives us a relative abundance of roughly 83%. As we notice, both of our percent abundances add up to our total, which is 100%. So we know that roughly 17% of all the isotopes in nature are going to be boron 10, while 83% of our isotopes will be boron 11. So this is sort of giving you a background on how percent abundance is calculated and estimated. Does it make sense to everyone, this idea that we have different amounts of each isotope in nature? Does that idea make sense? That we have different amounts of each isotope in nature, and each of those isotopes have a different mass. Any questions on this idea? So why is this important? Why am I going through and having you focus on this? Well, it has to do with the fact that this mass in the periodic table is known as the average atomic mass. Now, this average atomic mass, as its name implies, it does not match an exact isotope. It is the weighted average of the mass of all isotopes of that element, accounting for their percent abundance in nature. So, the way that I like to think about it, is that the average atomic mass is the sum, where you're adding up each of these quantities, of the mass of your isotope times the percent of the abundance of your isotope over 100. So written out longhand, this is probably the most comfortable equation that you'll be using for this class. The average atomic mass is the mass of your isotope times the percent abundance for first isotope, plus the mass of isotope 2 times the percent abundance of isotope 2, and you keep adding up the masses times the percent abundance until you've added up all of your isotopes. Don't worry if this equation seems a little complicated at first glance. In reality, it's relatively straightforward as long as you're careful with your calculator. So to show how this is applied in practice, let's look at an example. So let's look at our good friend chlorine that we've established. We have two naturally occurring isotopes, chlorine-35 and chlorine-37. So now we're gonna really analyze and read through this problem. And the first thing that we need is the mass of each isotope. So I'm gonna make two columns, chlorine-35 and chlorine-37. And what are we given for the mass for chlorine-35? What is the mass of chlorine-35? And don't be shy to type it in the chat or unmute and state it verbally. So the mass of chlorine-35 is roughly 35, but are we given a more exact value? Are we given a more exact value for our mass?
$34.97.
Yep, exactly right. And the units in this case are AMU, which is a unit of mass. It represents a very, very small unit of mass. This is the same unit of mass that we discussed when we talked about protons, neutrons, and electrons. So now for chlorine-37, what is the mass of chlorine-37? What would the mass be for chlorine-37? 36.97, exactly right. And it's 36.97 AMU. Don't be shy to unmute if you have any questions or if you'd like to share your response. The next piece of data we'll need, and I'll write this in a different color just to make it perfectly clear. The next thing that you'll need is the percent abundance. So what is the percent abundance of chlorine 35? What is the percent abundance of chlorine 35?
75.78.
Yep, exactly right. And what would the abundance of chlorine 37 be?
$24.22.
Yep, exactly right. So then we now have all the data that we need to plug into our average atomic mass. So the average atomic mass of chlorine is equal to the mass of chlorine 35 times the percent abundance divided by 100% plus the mass of chlorine 37 times the percent abundance of chlorine 37 over 100%. And now what we're going to do is we're going to punch this into our calculator. And in your calculator, you're going to want to enter each of these multiplication terms in parentheses. So punching this into our calculator, we have 34.97 times 75.78 over 100. So from the first step, you should get 26.500266 AMU. I'm just showing this as a placeholder. You're then going to hit the plus sign and a parentheses symbol. Then you enter the rest of your operation. 36.97 times 24.22 over 100. And then you're going to close the parentheses and then you're going to hit equals. So this first operation should give you about 8.954134. And if we add each of these components together, we get an average atomic mass equal to 35.4544 AMU. If we look at each of our numbers that we're adding together, each of our original numbers had 2 decimal places. So we round our final answer to 2 decimal places, which gives us 35.45 AMU for the atomic mass of chlorine. Is everyone able to receive the same result when they punch it into your calculator? Make sure to enter exactly what I've written in this equation. And you have to carry through all of the digits through your calculation. Otherwise, your average atomic mass will have a rounding error. Any questions on this example? you really want to try with your calculator and just make sure you can get the same results. Is everyone feeling comfortable with this? Is everyone getting the same results when they try to calculate the average atomic mass?
Professor, could you explain why it has only 2 decimal place?
Ah,
Because
yeah.
it seems like 3, 4, 5, 6 decimal place, the number we are adding.
Yes. However, the original number that was used in our calculations, so this original number here has a total of 4 sig figs since we're dealing with a multiplication and division operation. So
Right.
this final number here only has significant digits up to the 4th decimal place. Oh, sorry. It has 4 sig figs, and as a result, it has 2 decimal places.
Okay, got it. Thank you.
For this number, it also has 4 sig figs, and even though it goes up to the 3rd decimal place, we retain the least number of decimal places for addition, so our final answer will have 2. Does that make sense?
Yes, thank you.
Perfect. Any other questions on this example? Okay, so to make sure that everyone is comfortable with this, I'd like you now, given the following data for boron, I'd like you to calculate the average atomic mass for boron. And again, I'd just like you to solve this equation and solve this problem the exact same way that I showed you in the earlier example. So you're going to want to fill in the percent abundance and the mass, and then you can plug in your results into the average atomic mass equation. So I'd like you to take about 3 to 4 minutes and calculate the average atomic mass of boron. And don't be shy to share your responses in the chat or share any questions that you have in the chat. And you can always check your work by looking at the periodic table, finding boron, and reading off the average atomic mass. Let's try to get a few more responses in the chat, and we'll discuss in about 3 minutes. And don't be shy to share your responses in the chat, ask questions in the chat, or ask questions or share your responses verbally. And don't be shy to share your response even if it differs from your classmates. The more responses we have, the more I can get a sense of student perspectives in solving these problems and to provide feedback and more relevant examples. And we'll discuss in about another 2 minutes. And we'll discuss this example in another minute. Don't be shy to share your responses or to share your questions. And it's really important that when you're working through these problems, you have some of your work present. So that way, when we go over the solution, you can look at the logic that you've utilized and you can correct the logic that you've utilized, or just notice a calculation error that could be easily fixed. So we have a reasonable pool of responses. So let's now tackle this example. So reading off the percent abundance, and since this is the first example that we're doing on our own, we'll stick to the color coding. The percent abundance of boron 10 was 20.00. Boron 11 was 80.00%. We also know that boron 10 has a mass of 10.0129 AMU. Boron 11 has a mass of 11.009 AMU. Okay, so we have all the data we need to calculate the average atomic mass of boron, which in this case would be the mass of boron 10 times the percent abundance of boron over 100%. This is for boron 10, plus the mass of boron 11 times the percentage of boron 11 over 100%. That in turn would give us an average atomic mass equal to, and remember, when you're entering it into your calculator, you put each of these multiplication terms, each set in parentheses. So you'd enter exactly what symbol you see in my drawing. So how do we interpret that? Well, that means first I'm going to enter a parentheses symbol, then 10.0129 times 20 over 100. So from this first calculation, we get 2.00258. Following sig fig rules, this number should have 4 sig figs or 3 decimal places. Okay, then we're going to hit the plus symbol and then another parentheses. So we have 11.009 times 80 over 100. And that would give us 8.8072. So this number in this case has 4 sig figs, 3 decimal places. So if we add these numbers together, we get, for our average atomic mass, that in turn gives us 10.80978. We then round our answer following sig fig rules to the nearest decimal place. Since we're dealing with addition, we have 3 decimal places, and that gives us 10.810 AMU. Does this make sense to everyone? In this case, we have 3 decimal places because we're following the sig fig rules for each step individually.
Professor, I have a question on the top when you are, and I understand you first multiply the 10 point
Yep.
times 20, but then divide them by 100. Doesn't 100 have only 3 sig fig? We
So
don't look
the 100% is considered an exact number as part of the equation. If it makes it easier to visualize, you can write it as 100.00%. Essentially, the 100% that's shown in this equation is considered an exact number. It's never going to constrain the sig figs you can report.
Okay, got it. Thank you.
Any other questions on this example? If not, let's keep going and let's talk a little bit about atomic structure. So we have our fundamental particles, our positively charged protons, our neutral neutrons, and our negatively charged electrons. And Rutherford nuclear theory essentially focuses on how are these protons, neutrons, and electrons distributed in how are these protons, neutrons, and electrons distributed in our atom. So just as a reminder, this is from the chapter 2 notes, which are available on Canvas. So the key tenets for Rutherford nuclear theory are, first and foremost, most of the atom's mass and all of its positive charge are contained in a cluster of protons and neutrons called the nucleus. So this is our example nucleus. So the nucleus contains all of our protons and neutrons. Now, most of an atom's volume is empty space. So if I drew this very teeny tiny dot as our nucleus, the edge of our atom would be miles away. So the majority of an atom is empty space. So if our nucleus is just this very, very, very tiny dot, think of the rest of an atom's volume as mostly empty space. The nucleus is relatively small compared to the rest of your atom. So just to put it to scale, if this dot were the nucleus, your outer reaches of your atom would be miles away. Now, atoms are neutral, and there are an equal number of negatively charged electrons surrounding the nucleus and positively charged protons in the nucleus. So, for example, if we have 2 protons and we have a neutral atom, surrounding our nucleus would be a total of 2 electrons. Does this make sense to everyone? So for a neutral atom, we will have an equal number of protons in the nucleus and electrons surrounding the nucleus. Any questions for these tenets of Rutherford nuclear theory? Any questions for these tenets of Rutherford nuclear theory?
Professor, what are those empty circles you are representing?
These empty circles are describing neutrons. And the reason we
About
draw,
the proton?
the protons are the positively charged. So yeah, protons are positive, neutrons are neutral, which means no charge, and electrons are negatively charged. Does that make sense?
Yes.
Perfect. And remember the positively charged protons and neutral neutrons are found in the nucleus. The electrons surround the nucleus. Now, as you've been hearing from my explanation, the exact position of our electrons is not defined as clearly as it can be. And this brings us to our next model of atomic structure, which really focuses on how are our electrons arranged? How are the electrons arranged in our atoms? And this revised model is known as the Bohr model. So we still have the nucleus. We still have the nucleus, which contains our protons and our neutrons. Nucleus is relatively boring in a lot of these models. So the main feature of the Bohr model is the electrons will orbit the nucleus in discrete orbits, almost like planets. You can think of it like the planets orbiting the sun. Electrons in each orbit have a unique energy. So each of these orbits have a different and unique energy. And let's be more specific here, as a unique electron energy. And it also, just staring at these circles, we also see they have a unique electron position. Okay, so electrons occupy these orbits at a fixed distance from the nucleus with a discrete energy. Now, what we also know is that electrons that are farther from the nucleus are higher in energy and less stable. Well, that's because our electrons really want to interact and want to be close to this positively charged nucleus. The farther we are away from the nucleus, the weaker this interaction and the less stable our electrons are. So let's just put a note of that. So electrons far from the nucleus are high in energy. So another way that we can describe this phenomena is this idea that electron orbitals and electron energies are quantized. Now, it seems like don't be intimidated by this word, as it really represents quite a simple idea. When we use the word quantize, what we're saying is that our electron energy and electron positions are divided into discrete steps or increments. So when you think quantized, think stairs. So does everyone notice how these orbits are at certain distances? So we can theoretically move between our orbits, just like climbing up a set of stairs, but we can only occupy these discrete orbits, these discrete positions and energies. Does that make sense? Another analogy to help you visualize this, when you're walking up a set of stairs, you can't put your foot down in between. You can't put your foot down in between the first and second step. It doesn't work, right? You can only be on a defined step, a defined orbit. Does that make sense to everyone? Can I get some feedback in the chat? Any questions on this? So just as a summary for the Bohr model, the electrons orbit the nucleus almost like planets. Each orbit has a unique energy, and each orbit is at a fixed distance from the nucleus. Electrons that are farther from the nucleus are higher in energy. And the electron position and energy is quantized, which means it can only occupy discrete values, discrete steps. We can't occupy positions other than these discrete orbits in the Bohr model. Does that make sense? Any questions on that?
Professor, does it matter where in that orbit? We can just put it anywhere in that circle? Like let's say we're on the first circle.
Yeah, so as long as it's in this defined orbit, the electron can be anywhere in that orbit.
Okay.
It just must occupy one of these discrete orbits. Does that make sense?
Yes.
Perfect. So let's talk a little bit about the Bohr model in terms of how we can describe the electron. So as electrons occupy discrete orbits at a discrete distance from the nucleus with a discrete energy, we call these orbits energy levels. And the principal quantum number n describes the orbit. It indicates the orbit and the electron energy. So for example, n equals 1 would be the first orbit, and it's the lowest energy. N equals 2 describes the second orbit, and as it's farther from the nucleus, it's higher energy. So just think of n, the principal quantum number, as describing our orbit number. It describes how close our electron is to the nucleus and whether it's low or high energy. So the main thing that you need to know, large N means that we are far from the nucleus. And if we're far from the nucleus, that electron is going to be high in energy. Does that make sense to everyone? So just like steps in a set of stairs, we can only occupy discrete orbits with a defined value of n with a defined discrete energy. Does this make sense to everyone? Any questions on this idea? You'll see n again in our future models. Now, you may say, well, why is this important? Why does this matter? Well, the Bohr model is not perfect. The Bohr model is not perfect, but it starts to introduce ideas that find their way into the modern atomic model, which is the quantum model. And this is the model that you're going to be responsible for memorizing and understanding in detail, as this is the model that we're going to use to explain our electron energy and in turn start to explain electron reactivity and periodic trends. So the quantum model is the most recent model and has the greatest predictive power of all of these atomic models. And the quantum model is built on the following idea. So we cannot precisely determine the energy and the location of an electron. fundamentally, we can't figure out both the energy and position. So we're sort of stuck there. So instead of doing that, what we're going to do is for a given electron energy. So for a given electron energy, what we're going to do is we're going to describe the probability that you'll find an electron in that region of space. And we model this idea using what are known as orbitals. And an orbital describes the region of space that an electron of a specific energy is likely to be. So this orbital, these pictures that we're going to draw, tell us that for a specific electron energy, this is where the electron can or is likely to be. The best analogy that I like to use for this, although in the current times it's not as readily applicable, if you ever ordered an Uber, for example, you'll get your position and then it'll say somewhere in this region of space, that's where your driver is going to be. And it's this idea that, well, somewhere in this region of space, your electron is likely present. So an orbital essentially says, in this region of space, your electron of a very specific energy is likely present. Does that make sense to everyone? So to make this a little bit less esoteric, let's look at some pictures of orbitals. So each of these pictures represent different orbitals, where an orbital is a region of space where an electron of a fixed specific energy is likely to be. So somewhere in this region of space, we have our electrons. Now, orbitals are centered around the nucleus, and we have no electron density at the nucleus. So if we drew our nucleus in the center, so our nucleus is at the center of our atom. These orbitals, which are regions of space where our electrons are present, surround the nucleus, and there are no electrons in the nucleus. They're just surrounding the nucleus. Now, the beautiful thing about orbitals is that they closely mirror the observed electron density for atoms. So these orbital pictures can help us understand and help us rationalize and explain the behavior of electrons in reactions. And that's our goal in this chapter. And we're also going to use this model. We're going to use this orbital model to explain bonds and explain how compounds form and why compounds have certain shapes. Okay. So I know this seems a little weighty at first glance, but I just want to check. Is everyone comfortable with this idea of what an orbital represents? Is everyone comfortable with this idea of what an orbital represents? It's a region of space where an electron of a fixed energy is likely to be. Another visualization, another way you can think about this is an approximation, but it's an analogy that I like. Pretend that we have like a fly, and we've trapped it in this container. And somewhere in this container, the fly is likely to be present, but we don't know the exact position. We only know the exact energy.
So Professor, in the quantum model, we don't have the ends anymore. So we don't have first circle, second. It's just
So,
one. It might be
no.
somewhere.
The electron energy is going to be partially described by N, and we'll see N appear again in this model, but we have a few other quantum numbers to talk about. But yes, N still plays a role, and it's gonna have a dramatic effect, as we'll talk about in a moment, on orbital size and orbital energy. So yes, we will be seeing N again. And we'll talk about that momentarily. Is everyone comfortable with this model? Is everyone comfortable with this first idea? Any questions on this first idea? So let's talk a little bit about orbitals and quantum numbers. So electrons in atoms are found in principal energy levels, which are called N values, which are also called shells. So a shell is a row in the periodic table. So if we look at our periodic table, the first row is N equals 1, the second row is N equals 2. So we already have a direct link between the periodic table that we're oh so familiar with and these N values, which are part and integral to the quantum model. So the N, just like before, is the principal quantum number. And all orbitals with the same principal quantum number are in the same shell. N, just like before, controls orbital size and orbital energy. The larger your N, the larger your orbital. So if we look at this picture, we're comparing an N equals 1 orbital to an N equals 2 orbital. Which orbital is larger? Which electron is farther from our nucleus? If the nucleus is at the center, which electron is farther from the nucleus? N equals 1 or N equals 2? N equals 2, right? So our electron is farther from the nucleus. And sorry about that. It's farther from the nucleus, and as a result, because it's farther from the nucleus, it's higher in energy. Now, what's important to keep in mind is orbitals with the same N value have the same size. So we're going to start to see different types of orbitals. So this is an N equals 2 orbital, known as an S orbital. And we have another N equals 2 orbital known as a P orbital. Notice how these orbitals have the same N value. So they have the same size, but they have a different shape. And this different shape is a result of a different second quantum number that we'll talk about in a little bit. So does everyone understand what N controls? It controls orbital size, which is the distance of an electron from the nucleus, and it controls orbital energy. Does that make sense? Does this make sense to everyone? So N controls orbital size, the distance of an electron from the nucleus. Just like we saw in this first example here, as N increases, our orbital gets bigger, our electron is farther from the nucleus and higher in energy. N controls orbital size. So even if we have two different orbitals, if they have the same n value, they have the same size, even though they have different shapes. Does that make sense? Perfect. So now this is really cool. If we look at the periodic table, the periodic table actually perfectly maps onto our quantum model. So the principal energy level n. So each of our rows, so this would be n equals 1, n equals 2, n equals 3. N, a shell, is a row in the periodic table. Each shell is divided into subshells. So for example, this first set of two elements is known as the S subshell. The right 6 elements are known as the P subshell. We also have the D subshell and the F subshell. Each subshell has a different orbital shape, and each subshell is describing a section of a row in the periodic table. Subshells are defined by L, which is known as the angular momentum number. L specifies orbital shape. For any row, L can have values from 0 to n minus 1. So we'll show how this can play a role in how many subshells we have in a row. The main thing I want you to know is different subshells have different orbital shapes. So here's an example of each of our different subshells. So we have our S subshells, which are L is 0, which look like a sphere. Our P subshells, which look like a dumbbell, correspond to L equals 1. Our D subshells, which can look either clover shaped or like this example shown here, these correspond to L equals 2. And our F subshells, which correspond to L equals 3, have relatively complex shapes, and we don't commonly see the F subshell in this class. So subshells are parts, are regions of each row in the periodic table. Each subshell has a unique quantum number called the angular momentum quantum number, which describes our orbital shape. Does that make sense to everyone? Does this new quantum number make sense? L controls shape. Any questions on this idea? If not, let's try to tie this idea together, and I really want you to get a sense of what each of these orbitals look like and how many of each orbitals we have in a subshell. So each subshell contains a unique number of orbitals. So our S orbitals correspond to L equals 0. They're spherical shaped and we have one orbital. So in the S subshell, we have one orbital. For P orbitals, they correspond to L equals 1. These are dumbbell shaped, and we have in our P subshell, how many orbitals do we see? How many orbitals do we see in our P subshell? How many orbitals have we drawn? 3. So we have 3 orbitals. For our d orbitals, we have a lot more of them. D orbitals correspond to L equals 2. And in our d subshell, how many orbitals in total do we have? How many orbitals do we have in our d subshell? How many pictures do you see? We have a total of 5 orbitals. Does this make sense to everyone?
Professor, when you say 5, what are you counting? Those yellow things?
We're counting the number of unique orbital pictures. So we have 5 unique orbital pictures, so we have a total of 5 orbital. So an orbital is this picture shown here, which describes the region of space where an electron is likely to be present. So it's not the number of lobes in the picture, but rather the number of unique orbital pictures that we have for a given subshell. So we see 5 different orbitals, 5 different pictures, and that tells us how many orbitals we have. So like for example, for the p orbitals, we have a total of 1, 2, 3 unique orbital arrangements. So we have 3 orbitals in our subshell. Does that make sense? Did that clarify your question?
Okay, so we need to know if it's p orbital, they have 3 different
Yes.
possibilities. So that's all we need to memorize that, right?
Yes, and we're going to apply that and we'll help you be familiar. Well, the next idea will help you familiarize yourself with the number of orbitals in each subshell, because we're going to apply this idea to start to describe electrons in our atoms.
Okay.
So when we think about shells and electrons, we're going to talk about each shell. Each shell, which corresponds to a value of n, contains a unique number of subshells, which are L values. So the first energy level or shell, which is n equals 1, contains 1 orbital, which is our s orbital. If you're curious why that is, for n equals 1, we can have values of L equals 0, and that's it. That tells us we can have s orbitals. For our s orbital, which is L equals 0, we have 1 orbital. So in total, we just have 1 orbital in n equals 1. And we can see that in the picture that I've drawn, because how many unique shapes do you see? How many unique shapes do you see in n equals 1? How many unique shapes do we see in this first drawing? Just 1. Does that make sense? Now, just superficially here, if we look at the second energy level or shell for n equals 2, how many total unique orbitals do we see? How many total unique shapes do we see? 4. So we have 4 orbitals present. That's because for n equals 2, we can have L equals 0 and L equals 1. L equals 0 are s orbitals, where we have 1 orbital. And L equals 1 is describing our p orbitals, where we can have 3 of our p orbitals in that subshell. 1 plus 3 gives us 4. Does that make sense? Is everyone comfortable with this idea? So we're starting to outline how many orbitals we have in each shell. Is there a question I can address relating to this? Is there a question or is there a part that I can explain in more detail? So let's look at a third case now. When we're in the third energy level or shell, this is n equals 3. Now, how many pictures do we see? How many total unique orbitals do we see in n equals 3 in our third shell? 9, yep. So we have 9 total orbitals. That's because for n equals 3, we can have L equals 2, 1, and 0. L equals 0 is our s orbital, where we have 1 orbital. L equals 1, p orbitals, just like before, we have 3 of them. L equals 2 corresponds to our d orbitals, and we have 5 of them. Adding them up, we get a total of 9 orbitals in this shell. Does this idea make sense so far? Does this idea make sense so far?
I'm not understanding how you're getting the L numbers.
So each L is matched and correlates to a unique orbital shape. So the s orbitals, which are spherical, are in the L equals 0 subshell. The p orbitals are directly matched and are found in the L equals 1 subshell, while the d orbitals are found in L equals 2. So the L value directly matches the orbital shape and the subshell. Does that make sense? So depending on the type of orbital, it has a different L value. The s orbitals are L equals 0, the p orbitals are L equals 1, and the d orbitals are L equals 2. Each shape has a unique L value.
Okay, thank you.
I'm sorry, Professor, I don't understand how you get the 5 orbitals.
So for the D subshell, how many unique orbital shapes do we have if we count them up?
3, 4, 5. Okay.
And now adding up these 5 orbitals in our D subshell with our other subshells. So we take 5 and we add these remaining 4 orbitals to get our total. What's 5 plus 4?
9.
Exactly right.
Okay.
So this tells us how many unique orbitals we have in the third shell, in the third row.
Thank you.
Perfect, perfect. Any other questions I can address?
Professor, whatever number of n we have, always L is 1 less. That's how we know. Like, how do you know the L is 0, 1, 2? How did you get that L?
So L ranges from n minus 1, and then you count all the L values until you reach 0.
Got it. Okay. Thank you.
So now what we're going to do is we're going to tie this idea of orbitals directly to the periodic table and to our electrons. So I know this seems esoteric at first, but now we're going to start counting electrons. And what we're going to discuss now is this idea that each orbital can hold a maximum of 2 electrons of opposite spins, and we draw our electrons with an up arrow for a quote unquote up spin, a down arrow for a down spin. What I need you to know is that each orbital can hold 2 electrons. Okay? Each orbital holds 2 electrons. Now, what we're going to do is we're going to figure out how many electrons are in a subshell. How many electrons are present in each subshell, each unique value of L. So to do that, we're going to count the number of orbitals, and then we're going to note that we can have 2 electrons in each orbital, so we're going to multiply our number by 2. So the S subshell, L equals 0, has 1 orbital. So if we have 1 orbital and we have 2 electrons present, and we can have up to 2 electrons per orbital, we can hold 2 electrons in the S subshell. Does that logic make sense to everyone? We have 1 orbital, we can hold 2 electrons per orbital, so we can have 2 electrons total. That's why in the periodic table, when we look at the S subshell, it consists of the first 2 elements in that row, because we can hold 2 electrons in our S orbital. More on that later. The P subshell has 3 orbitals, 1, 2, 3. So if we have 3 orbitals and we can each hold 2 electrons per orbital, we can have 6 electrons in our P subshell. And that is why when we look at the P block in the periodic table, it is the last 6 elements. So we're starting to see a connection. It's developing here between this quantum model, the number of orbitals, and the arrangement of our periodic table. Does this make sense so far? Does this make sense so far?
So Professor, when you say the last 6 elements,
Yes.
you're speaking about the boron to the neon, those last 6?
Exactly right, yes. And we're going to start to map these subshells, match these blocks in the periodic table, and we're going to draw them out in our periodic table momentarily. And this is why different atoms are grouped in different ways in the periodic table, because their behavior depends on where the electrons are located. What shell are the electrons present in? Very good question. Let's talk about the D subshell now, which is L is 2. We have 5 total orbitals. So we can hold 10 electrons. So we have 10 electrons, and that is why our D block, otherwise known as our transition metals, that portion of the periodic table contains exactly 10 elements. So is everyone comfortable with the number of electrons in a subshell? Is everyone comfortable with the number of electrons in a subshell? Any questions on this? So let's take this and let's now look at how many electrons can we have in a shell. Now there's an equation you can use. The maximum electrons in a shell is 2n squared. That's one way you can calculate the maximum number of electrons in a shell. I don't like that equation personally because I find if you get used to counting orbitals, it will help you remember and help you retain the orbitals in each shell, and it'll allow you to tackle later problems in this chapter more easily. So the first energy level, n equals 1, we've seen this idea before. It has one orbital. So n equals 1, we just have our s orbital. So since we have one orbital, and each orbital can hold 2 electrons, our first n equals 1 shell has 2 electrons total. And that is why in the first row of the periodic table, we only see 2 elements, because our first shell can only hold 2 electrons. Is this starting to come together? Is it starting to make sense? Are the pieces starting to fit together?
Professor, for the transition element, for example,
Yes.
so if we pick one of those, let's say like Ni, so it says the number 28 on the top, right? So
Yes.
that's 28 proton, right? So it has 28 electron, doesn't it?
Yes, that's true. And you're actually leading into the next part of our discussion, where once we have each of our shells and subshells, we're going to talk about how electrons are added to each shell and subshell and then we can use these electron diagrams to describe our atom in detail.
Okay, got it. Okay, so I wait then.
So we'll definitely get to it, and that's a very good point that you're leading up to. The second energy level or shell, n equals 2, contains 4 orbitals. We have our s orbital and our p orbitals. So if we add up our total number of electrons, so we have 4 orbitals, we have 2 electrons per orbital, that gives us 8 electrons total in our n equals 2 shell. And the way I like to remember it, is if I look at the periodic table in the second row, how many total boxes do I see? How many total elements do I see in my second row? 8, exactly right. We have the S block elements and we have the P block elements. In total, we can fit 8 electrons in that shell, and that's why 8 elements are in that row. Is this starting to fit together? I find this is why the periodic table is so useful, because if you keep it when you're reviewing these topics, it can provide you a framework to organize your thoughts. Any questions on this idea? So finally, the third energy level, or the third shell, contains 9 orbitals, and thus it can hold 18 electrons. So we have 9 orbitals, 9 times 2. So for our n equals 3, we can hold a total of 18 electrons. So is everyone comfortable with the number of electrons in a shell? The number of electrons maximum in a row of the periodic table. Is everyone comfortable with that idea? Any questions? Okay, so let's try to play a little bit of a game here, and let's fill in the blanks. So a 3p orbital, is in what shell? First, second, or third? So when we dissect the 3p, the number in front is our n value. This says n equals 3, which describes our shell. The p orbital tells us our L value, and p is L equals 1. That tells us my subshell. So to answer the first question, a 3p orbital is in the third shell because we're n equals 3. A 3p orbital, so each orbital can hold how many electrons? So can hold 2 electrons. Yep, that's exactly right. So just be careful when you read the question to differentiate between orbital, shell, and subshell. Those are talking about 3 different things. So what I want you to do now is I want you to play a bit of a fill in the blank game for each of these 3 problems. And I'd like you to share your responses for each of these fill in the blank comprehension checks in the chat. And if you have any questions, don't be shy to ask them in the chat. Make sure you're highlighting the keywords that you need to answer each question. You should be familiar with what a subshell, shell, and orbital is describing. So we'll take about 5 minutes on this example, and then we'll come together as a group to discuss. Don't be shy to share your responses in the chat or verbally. And if you have any questions, don't be shy to share them in the chat or ask your questions verbally.
So for the second one, the second subshell contains or I guess the third one in this case, contains the L and 1 orbital. Is that?
So when we're talking about for the second subshell, so there may not be more than one. So when we think about subshell, this is referring to a value of L. So for this first example, so the second subshell, so the second subshell in this case, so for our subshells, we have the S and P subshell. So the P subshell, so the second subshell contains just the P orbitals. And the second subshell, which is our P subshell, can hold a maximum. So for our P subshell, we have a total of 3 orbitals, and we can hold a maximum of 3 times 2 or 6 electrons. So in some cases, for these fill in the blank problems, you may not have to fill in all of your blanks. Does that make sense?
Yes.
Perfect. So let's keep working on these problems. Thank you for that question, as that was very helpful to help provide some guidance for some of these fill in the blank problems. And let's keep working on these examples, and don't be shy to submit your responses in the chat, and I'll provide feedback once I see some responses. And if you have any questions, I'd be happy to answer them in the chat or verbally.
Professor, could you please roll it up for a second? I want to take a picture of that top line. Right. Thank you. Just right there. Thank you. Thank you. I'm done. Thank you.
Yes, perfect. And don't be shy to ask questions or to share your responses in the chat. And don't be shy to share your responses in the chat or even ask a question. That alone can be very invaluable and help clarifying this concept. So keep in mind that when we use the word shell, we're talking about N. And subshell is talking about L. And don't be shy to submit your responses in the chat. Let's try to get a few more responses or a few more questions before we discuss in about 2 minutes. And really don't be shy to share your response, as it can help me get a sense of how students are working through these problems and to get a sense of any clarifying information I can provide. So let's play a fill in the blank game, and I'm going to need everyone to help me out here. The 2s orbital is in what shell? So what n value does a 2s orbital have? What value of n are we talking about? 2, yep. So it's in the second shell, okay? And a 2s orbital. So if we just look at an individual orbital, how many electrons can we hold? How many electrons do we have per orbital? 2, yep. Perfect. Shell refers to n, which is the number in front. Subshell refers to L. So when you see the word shell, think n, number in front. Subshell talks about L. So if we look at our subshells, we have our S, P, and D subshells. The first subshell is what? The first subshell has what orbitals? The first subshell, the first of our list. What orbitals are found in the first subshell? S. Exactly right. And in the first subshell, when we're looking at the S orbitals, how many electrons can be found in the S subshell?
Two of them already. I don't want anymore.
How many electrons are found in the S subshell? 2, because we have one orbital. So the S subshell can hold 2 electrons. Do these examples make sense to everyone so far? Any questions on these examples so far? So we'll stop here for today. just as a preview for next session, what we're going to talk about next session is we're going to focus on taking each of these cells, shells and subshells and arranging them in order of energy, and then using these orbital diagrams to explain and describe how electrons are arranged in atoms, and in turn, we're going to use it to explain common patterns of reactivity. So that's our plan. What I'd want you to be familiar with from this lecture is you should be familiar with each of the shells, which are the rows, and the subshells, which are the sections of the periodic table. And you should be familiar with the three different orbital shapes and three different orbital subshells that we covered today. And you should be familiar with the number of electrons in each orbital and each subshell. That'll be used extensively next class period. So I'll stop the recording.